I suggest you read the subheading. Okay. For the non-Turkish speakers, I hope the crude translation tells you something. Does it?
Yes, it does.
Well, just like many things in life, there is no single solution, no single truth. I am going to show you what I did. Well, essentially this morning, during other lectures. This is not the only way, this is not the best way, this is just a way. So let's start. For the analysis part, those of you who are the first timers will be spoon-fed now. But tomorrow, of course, you are expected to eat by your own. Okay. Now, we start by looking at the, remember, where did we leave? We have managed to generate two root files, one containing the events for signal, and the other one containing the events for background. Both root files were made from LHCO files. Therefore, the event format is the same in both files. This is important. There is something that we discuss often, especially with Gökhan and Erkcan. The best is to have your analysis on your laptop so that you can work all the time and everywhere, whenever you are not doing anything else. We call this, well, people call this, including me, a laptopable analysis. So it's important to have things laptopable. That means you have it with you at all the time. You wake up in the middle of the night, you pull your laptop to yourself, and start working. Anyway, so we start like this. We saw many things in the root lecture, and we are going to use these things. For example, we know how to load the events into root. Actually, there is an easier way. You say root, and then give the name of the root file. For example, root si for signal.root that we have generated. Then it will load the files. We have also seen this command which would make two files, generate two files. LHCO is the name of the tree. You give the command make class, and the name of my class is estop_a for estop analysis. Right? This thing is going to generate two files. One estop_a.c, the implementation, and another one .h for headers and all the other definitions, variable definitions, branch definitions, etc. So, how do we start? We start by editing this estop_a.c file. And if you manage to generate such a file and open this with an editor, you will see that it's basically empty. It has nothing in it, except some comments at the beginning which tells you how to run this file. Okay. So within the file, you find the information about how to run it. Very good. So we start adding few things. We start by declaring some histograms, one-dimensional histograms that we are declaring here. What am I declaring? Let's see. J mut, L mut. What do you think these are? Obviously, jet multiplicity, lepton multiplicity. Then jet eta, jet phi. Eta of my jets, phi of my jets. Jet pt, missing et. But they are just declarations. Nothing is defined here. The definitions are here at the bottom. By the way, I have tried to upload the slides on the page. I hope they are uploaded now. Nevertheless, I'm going to correct a few things and re-upload later on. I will fix a few things which are still in Turkish. Alright, definitions. Okay, I learned how to define a one-dimensional histogram. It's a histogram with handle J multiplicity. The name is written here explicitly, and since this is a counter, I define the number of my bins to be 20, and I'm counting also the zeros, so I start from minus 0.5 up to 19.5, something like that. I do the same thing for electrons here, or I should say leptons. It is called L-bool and lepton multiplicity. 8 of my jets, I have divided the range, eta range to 50, and the eta range ranges from minus 5 to plus 5.
So is like number of jets in a single event?
We will see how we fill that. Just a second. But indeed, it will be the number of jets in a single event. So jet phi, jet pt, missing et, they are all defined. And also, I have tried to write these things carefully so that later on, if you need to write in Greek letters, you know how to do hash, and if you need to do subscript, you know how to do. These are, in a sense, very similar to LaTeX commands. All right? Now, by looking at this notation, you understand how we would write T subscript T out. Now, as I said, the main file, these we write at the top of the file, right after this return statement. Now, the minute in quotes, is going to be also very simple because we are starting simple and we are going to step by step evolve. And here in the slanted box is the main meat. There is this thing called an event loop in the file. You are adding basically 2 lines. You are filling a histogram, JMOOT, that you declared here, defined here. You are now filling it with this variable, jet underscore, with an uppercase J. How do I know such a variable exists? I know because all the variables are listed in the header file. Estub underscore a dot h contains all the variables that I can use. What are these? For example, jet underscore tells me the number of jets in the event. For each event, they are different. Muon underscore tells me the number of muons, or muon candidates, muons, in this event. It changes every event. Electron underscore is the same thing. Alternatively, you can load the file into root, launch your T browser, as you have learned today, and then look at the names of different trees, leaves, etc. You can also do that. Whatever you see in the root file is going to end up in the header file as a variable. Why? Because the header file and C code are all prepared by root using this make class command. Right? So we have generated our class, analysis class, to look at the variables in the entropy. You following, or you are lost in the slides? Maybe it was a bad idea to upload the slides. Listening? You don't care? No. You can. Okay. Now, obviously, you fill your histograms in the event loop. Oh, by the way, we will have a lot of curly braces. And it is a good habit that I suggest you pick up to write as a comment after each curly brace which loop it is ending. Maybe it's old-fashioned, but I find it very useful. So I wrote here that this is the end of my event loop. So what do? For every event, I am filling jet multiplicity and lepton multiplicity. Not very complicated. Huh? You should be able to follow this. Now, after my event loop, in this last curly brace, the root program ends. So right before the end, I say jet multiplicity draw. I want to see the histogram. But once the event loop is complete, I want to see, not before.
But why don't we just fill the tree instead of making histograms already? Because from a tree, it's really easy to make histogram anyway. Okay.
Okay, so now, how do I run this beast? This beast will be run by loading the macro. Root C codes are called macros, as you know. Within root, I say .l for loading without any execution. Name of the macro, which is estuff _a.c. So now I have loaded this class. This command instantiates this class. Estuff a class now has instantiated as something called easy analysis. I hope the name helps at least. Now I can execute all the commands belonging, all the functions belonging to estuff analysis through this easy analysis. So I say easy analysis arrow loop. Why? Because it's a pointer. When I run this loop, the event loop will be run automatically. Histograms will be filled, and as the last step, this plot is going to be made. Now, let's look at this plot. First of all, you see that the legend is somewhere unusual. If you are not accustomed to root, know that you can pick up objects and move around in the canvas. That is a useful thing to have. And we were expecting one plot only, and we have found only one plot, which is also nice. And then, concerning the number of entries, we read here 5,000, and I said, okay, why? Because if you go back, well, number of events when I was editing things, you can find it was 5,000. So out of my 5,000 events, I did a loop. I ran over my 5,000 events, and I filled a histogram. So since I have started with 5,000 events, and for every event I am filling the histogram once, I was expecting 5,000 entries, and here I find. One second. And what do I see? So this is the jet multiplicity as I filled it. And since I had put this in a clever way, I am seeing that a large number of events are with 2 jets, as I was expecting. Small number of events have 1 jet. Very small number of events have 0. And very small number of events have 3 jets. So here and here, my detector, my simulated detector was not good enough and missed some of the jets. And here, my detector or jet reconstruction algorithm, which you can select by the way, took other objects as jets and decided that there were 3 jets in the event. Yes, you had a question. Sorry.
Is this signal or background data?
At this point, I think when I took the screenshot, I was looking at the background. Tell me, why?
Sorry?
Should that matter?
I'm just curious.
No, it should not matter. From the jet multiplicity, it shouldn't matter. Alright, so far? No, not alright. What's wrong?
X-axis, what's this?
What is x-axis? Okay, x-axis is the jet multiplicity in the event. 0 means there were no jets in that event. When you look over the event, you look at the event. Listen to me. You look at the event, and then you put here 1 item if there are no jets in the event. Here you put one coin, okay? If there are 1 jets in the event. Here you put 2 coins. Here again you put 1 coin if there are 2 jets in the event. And at the end of the event loop you count. In each box, how many coins do I have? You understand that? Okay. Is it easy? Alright. Now, I have done something very basic. Nevertheless, very, very useful. I managed to loop over my events. I have managed to loop. I have managed to book a histogram, fill a histogram, and draw a histogram. So now life should be easier, right? Now, let's define more variables. I am going to define a quantity called jets as a set of Lorentz vectors, size 5, y5, a number, a large number. Could they be 64? I don't care. Sorry? I have defined a variable of type Lorentz vector named jets.
Lorentz vector?
Lorentz vector is the type, just like integer, float. Okay? the name of this variable is jets. Then I have defined here also another variable called mjj, mass of my invariant mass of my two jets, and it is going to be a Lorentz vector as well. Just before my declarations. Then, maybe the interesting thing to look at would be the properties of jets. So remember, I was using jet underscore as the counter of my jets. It tells me how many events I have in that jet. So I'm setting up a for loop. I am filling the Lorentz vector, jets, for each value of my index using this function, set pt eta phi mass. And for my each jet, I am sending in the pt of my jet, eta of my jet, phi of my jet, and mass of my jet. This is also easy, I guess. No? Yes? I'm confused. I am confused. I don't understand what we are doing. I'm following.
Could you repeat once?
I repeat once more. I am here in an event, in the event pool. Now I know that I have a number of jets, jet underscore number of jets. Now I'm looping over my jets, and I'm filling an array of Lorentz vectors called jets, and I am initializing with the pt, eta, phi, and mass of my jet. Why do I do this? Because this Lorentz vector class has many useful functions. For example, if I want to look at the eta of my jets in a histogram that I had declared and defined, I simply ask this variable jets, its eta, its phi, its pt. I can ask many things. Okay, I have filled these things in, but I can also do additional things that we will see.
So it's a building function. Let's say pt eta phi.
Indeed, it is building this variable jets.
So it's built-in function of the T Lorentz vector, right?
Yes. It's built-in function of the Lorentz class, T Lorentz vector class. Yes. Okay. Now this is the end of the for loop down here, and I do something else. Since I am focusing on the two jet final states, as you remember, I said if the jet number is different than 2, continue. This is a simple, very, very simple cut. Here, continue means go to the next event. Do not work on this event anymore. This event, I don't care anymore. Skip. Okay?
I have a question.
Yes?
For the jets E line, the first, yes. For this line we have 1, 2, 3, 4, 4 variable.
Yes, 4 quantities that you
4
sent
quantities, yes.
Yes.
But how put the 4 quantities is one parameter? This is a vector, but
a Lorentz vector is a Lorentz variable, is a Lorentz object.
4 dimensions.
Is a 4-dimensional object. Yes. You could have also initialized through px, the 3 momenta plus energy.
Yes.
But that I have chosen to initialize like this. Just as a surprise. Yes.
Are the function of
Jet pt, jet eta, jet phi. These things, these lines. Yes, they are readily available functions of the Lorentz class. If I had initialized through px, py, pz, and e, it would be very easy for me to get like this. Now, assume I want to plot, for example, px or pz in the same way that I extract pt. I would extract this px, pz, whatever. Okay. Yes.
Can you explain again this jet's number is equal to 0 if then we continue? You said that's
okay, let's look at this line once more. Jet underscore was the number of jets, and I want to reconstruct my W with 2 jets. Therefore, if I'm going to do any jet reconstruction after W prime reconstruction afterwards, that means I need at least 2 jets. And it's better that I don't consider 3 jets because I want to focus on 2. So I want to study only these events with 2 jets. The rest I don't care. So I say continue. Continue means go to the next event. Skip this event. Don't work on it anymore. In any case, this is the end of the event loop. There is nothing else to do. But we will add. Alright? As I wrote here, this is the 2 jet requirement. So, now I want to plot more things. That means I need to define a window. In root terminology, a canvas. This is how I define a canvas. I'm going to call it C1 for canvas 1. The header should be invariant mass plots. Well, I have invented that. These are the coordinates on screen. You can look at it if you want. You can put it in another location if you want. This is X, this is Y. So it will be it will be starting right from the edge of my computer, but 150 points to the right hand side. Anyway, this is not very important, but this is important. It says divide the canvas into 4. Divide 2, 2. I'm going to have 4 areas in which I'm going to put 4 different blocks. And then I draw the canvas. I do this right before I start to analyze the entropy. Alright? Now, if I want to plot more histograms, the ones that I have filled in, what do? At the end of my event loop, I do this. From canvas 1, go to the first box, which is here, draw the jet multiplicity. Then go to the second box, which is here, draw the jet eta, and go to the later on third box, which is here, draw jet phi. Not very difficult. You execute, and then you get the plot. Not very difficult. Yeah? Yes?
I don't understand. The eta, jet eta. Why? Because of phi symmetry, but eta not.
You are asking why this distribution is like that. Because you are hitting a massless particle. And the outgoing particles are one heavy and one neutrino. So the jets are following. The jets are coming from the W and they are following one of. They have a preference because of it. 3D. Now we should get ready to prepare the 2-jet invariant mass. That means I am adding one more declaration, one-dimensional histogram again, jet mass. I also add a definition after the missing ET definition. Okay, invariant mass. I want to zoom in. Now I was looking at the background. Now I am sure I wanted to see the main background, which was the sun and not the W. Therefore, I have restricted the boundaries to be from 0 to 200 so that I see the W correctly. Then we calculate. Now, I am now adding after this continue line. If the execution of my program comes to this point, that means I already passed this statement, means I have 2 jets. Alright? Therefore, invariant mass of my 2-jet sample, which is another Lorentz vector that I had described, is now obtained by adding these 2 jets. Look at the plus sign. I'm adding 2 Lorentz vectors like I was adding 2 integers. Very, very useful, this Lorentz plot. Then I'm filling in the mass of my 2 jets, JJ mass, filled with the mass of this dijet object, with the reconstructed dijet object mass. I put a dot m, parentheses, open close, and you have the invariant mass calculated by the Lorentz vector class. Isn't that cool? Fine? Now my 4th box was empty. I will put there the invariant mass of my 2 jets, run again, and I will end up here. And the peak, as you can expect, is around, well, if you can read this, it will be something like 80. Since I was looking at my background sample, it will be directly the invariant mass of the W book. Yes? No? Confused? Following? We haven't done anything about it yet. Yes?
I can't understand why we some Z0 and Z1 for the background.
We are now running on the background, but eventually we are going to run on the signal as well. And we said we are going to discover the W prime from the 2-jet channel. We are going to sum the 2 jets, which are the decay products of the W prime, and we are going to find the W prime. That's the idea. You understand that? No? Look, my W prime, where is my W prime? My W prime is decaying to 2 jets. Correct?
Yes.
Yes. Now I'm going to sum these 2 Lorentz vectors, 2 jets, to get the W prime.
Yes.
But I have started for some reason to work with the background.
Yes.
No obvious reason. I had that rule file. I started to work with that. No other reason. Okay. Now, finding the needle in a haystack, as they say. Usually, as an experimentalist, your task would be to get rid of the unwanted things, noise, otherwise known as the background. That means anything else giving same signal as your goal, whatever that goal is. Similar to the thing that we want to study, but something else. You want to listen to a radio channel, but unfortunately, about the same frequency, another radio channel is emitting another program that you don't want to listen. So that second thing is your noise, is your background. Hence the same thing. In our lingo, signature similar to what we are searching, but not what we are searching is a background. We are searching for a W prime, and we want to eliminate anything else that would look like it, but it isn't. In most of the beyond the standard model searches, standard model is a background. Therefore, we need to be able to separate all these junk and find this. What is a good, so these are cuts, selections, criteria. In this problem, finding the needle, a good cut would be what?
Magnet.
Yes, bring in a giant magnet and your problem is solved. Yeah. So what is the magnet? What is the giant magnet in this case? For example, we could use these properties. W prime is heavy, as we have put in the model. So the decay products, which are the jets, would be energetic, meaning they would carry high transverse momentum. But we can't use really this invariant mass of the 2 jets because this is in fact the quantity that we are searching. We can't apply cuts on the quantity that we are trying to measure. We have to apply cuts on other quantities. Yes.
Can we calculate invariant mass directly by some 2 jet mass?
But that's what we did.
Yes, we did.
Yes, that's what we did.
Is it proper?
Yes.
I mean,
What else? How else? I remind you your final lectures, decays. How were you doing? Were you doing your homework? No? You learned by hand how to do this.
yes, but
A decaying to B plus C. A has decayed to B plus C. Now I'm adding B and C to get back to A. Same story.
shouldn't we calculate energy minus energy square minus?
But internally the T Lorentz class is doing that already. You simply say plus, but the Lorentz class knows that these are Lorentz objects and does the 4-vector calculation.
So this is simply S, no? Here.
No, there is also the neutrino, not really. Bon. 4. We can also draw the jet VT and finally record the image. Because every time taking a screenshot for me was painful, I decided to save the image. And also I did a bit of reordering in here. For example, in the first box I have put the jet multiplicity, second box eta, but in the same box I wanted to draw phi as well. And since I am going to draw in the same box, I want to draw with a different color. And this is how you set the color. Option 2 refers to red. How do I know by heart? Don't ask. On the third box, I am putting the dijet invariant mass. On the fourth box, I am drawing the PT of my jets. And then this is how you save. And I have decided to save the file as analysis.jpg. Whatever you write here, JPEG, PNG, PS, whatever, root understands and saves in that format. You can also save the histograms that we have created. What interesting histograms have you created? For example, JPT is interesting, and dijet invariant mass is also interesting, I think. And whenever you see in my programs variables like AABB, AAA, BBB, that means they are temporary variables like Pippo in Italians or spaghetti they use oftentimes, whatever. I don't know what the Germans are using, for example. It's a temporary variable. Junk. For me, they are AAA, BBB. Alright. So this is how you open a file, results.root, and every time you write the histograms that you have calculated and close. And also every time you saw how I was loading. I launch root with the arrow keys, I load the class, I instantiate, and I do a loop. That is also taking a lot of my time, which I would like to avoid. Therefore, now I have written a small macro called runme.c, which would do exactly those things. You can tell root to load this macro called estub_a.c. Now, the name of the instantiation of the class doesn't need to be easy analysis anymore. That was for you to help. Now I'm going to call this SI for signal, and I'm going to say loop over the signal, and then return. When you do this, you get a float like this, and this is how you execute. It tells root to execute this runme.c and then quit afterwards. When it quits, two files are written out. One is the JPEG file for the analysis plots, and the other one is the results.root, which is histograms that I'm interested in. Still all right? Now, whenever I apply cuts, I ask how many events I am losing because of the cuts. So I'm cutting something really. What happens? Well, it would be useful to keep track of this number of lost events, because cut efficiency is something that we try to optimize in our analysis. From Jörg's lecture, you saw how you get a good efficiency of selecting signals and eliminating backgrounds. We discussed about boosted decision trees, cut-based methods, multivariate analysis, etc. We are going to see an example, a trivial example of a cut-based analysis. Now, to do that, we define another one-dimensional histogram called F, efficiency. And, well, okay, I could do this in another way, but I defined just 16 different cuts, a number. And then this is to help the eye to guide you, and also to prove the point that the bin labels do not need to be numbers. They could be text as well. So in this efficiency, my first bin will have the name all, because I want to count the events. The second one will contain 2 jets, the third one missing ET, and fourth one jet PT. Alright? Lost? Alright? Following? Lost? Tell me if you are lost. Tell me if you are following. I need to know. You are following. Now, to use this efficiency, at the beginning of my analysis, before I fill all these jet and lepton multiplicities, I count the number of events. I put in the first bin a coin of this efficiency histogram. Alright? Then whenever I do a cut, like you see, like you know, as we have done before, I put another coin in the second box. Therefore, I'm going to ask this question. I have started with how many events? Well, I'm going to look and find in box number 1. And how many events did survive after this requirement? Well, I'm going to see 2 in box number 2. In fact, I know this because I have been calculating, or I have been plotting the jet multiplicity all the time. So out of 5,000 events, if you look here, this is the number of events with 2 jets, about 3,400 or so were with 2 jets. So the efficiency of this cut will be 3,500 divided by 5,000. Yes? Not too difficult. Where were we? There we are. Okay. So therefore, this box now is counting the events surviving the 2-jet cut. And similarly, you can get the missing energy like this that you were asking you. And then here I apply another cut. For example, I require a minimum missing energy of missing transverse energy of 20 GeV, and then I'm counting the events which are surviving this cut, right? Now, so far I have worked on one particular type, signal or background. Now I am going to do something slightly more complicated and use a single macro to work on both event types, signal events and Monte Carlo events. To do that, I have to edit the header file, which I haven't done so far. So what do? This is the original form of the header file, and from here, I am going to go to this setup. What do? Why do, and how do? First of all, I need to tell the computer, now look at the signal event, comma, semicolon, now look at the background events. How do I tell them? Well, I think I'm going to use a string, which is a character, character array, CNAME, fixed length, because I'm lazy. No pointers, strings, I'm lazy. 128 characters. So as you see the difference, here the root 3, T3 was initialized. Now I have added two words to the same line. So when I initialize my class, I'm going to say whether I'm initializing for signal or for background. Understood? The same thing for loop. When I'm running on a loop, when I loop over the events, I should be able to say whether this is signal or background. And here, the default is something called, I invented something called generic, because I need to specify something. Okay. So these are mostly declarations. The definitions are in the C code. This is the header file. Remember, we are modifying the header file. In the header file, maybe there is one thing that we need to change. Well, not maybe, for sure. It's the initialization of the class. What to do in each case. And this is at the bottom of, well, further down in the header file. And this is the initialization of the class. And as I have written here, an array of characters of 128 bytes. Here is the same thing repeated, the same. Now, here is the main meat. What to do in this case? Very easy. So, I define a chain. What is a T chain? That means I'm going to look at different root files and I'm going to add them together. I might have multiple files, SM1, SM2, whatever. I'm going to chain them together and loop over all events in all root files. That's chain is something to help me to do that. All right? Now, when I initialize the class, I am sending in the variable that I'm going to use, which is the CNAME. Now, I'm doing a string comparison between the value that I have sent in and something fixed called SM. In this case, I am adding SM.root in my chain. Otherwise, I'm doing a string comparison between what I have sent here with SI, for signal obviously, and if this is true, I'm adding SI signal.root to my chain. And then I'm initializing my tree. So when I initialize this class, I have to say either SM or SI, otherwise it is going to crash. Okay, I haven't put any protection because I'm lazy. But if I do put in SM or SI, I'm going to analyze different things. Very easy, no? Very easy. You can't say you don't understand. This is very easy. So I need to edit the C file as well and propagate the modification that I have done for the loop character name. Now this is also only at the beginning when I was doing loop in the original file. This was empty. Loop open parentheses close parentheses. I have added the same thing, CNAME, 128 characters. Since now I have received whether this is a signal or background, I can make use of it. How? For example, when I'm saving the histograms, instead of saving results.root, I can save with something called whatever I send in, SM or SI. It will appear here. Again, my favorite dummy variable AAA. It is going to be that either SI minus out.root or SM minus out.root. And then the rest is exactly the same. Understood? Confused? Please say something, I beg you. Speak.
Where is S?
Where is S? Which S? This S. This is string print function. It prints this string inside this variable, temporary variable AAA, and when the function is called, %s is replaced by CNAME. CNAME is received in this loop coming from the initialization of the class. So obviously I need to modify the initialization as well. And this is my new run me. I again load my macro as before, but this time I instantiate twice, one with the name SI, one with the name SM. Yes? And then I loop over the signal with name SI, and I loop over the background with name SM. So these SI, SM, the background, etc. could be confusing, but it's really not. This SI and this BG, the classes themselves, the instances, they could be anything. I could call it ABC. I could call it signal. This, however, strings that I have sent in at the initialization should be the ones that I am doing a string comparison in the header file. Therefore, here I should either say SI or SM, nothing else. And here, this could be in principle anything. It is going to be only used when I output my calculated histograms into a root file. Right? I am lost completely. You lost me. Oh, Where were you lost?
In the course?
That is not a real hint, right? Well, sorry. Let me go forward, but I will discuss that during the party. Yes, you run this as before, and then okay. Well, as you see, I was running it today, and this is a screenshot from my VirtualBox. We start with sm.root, si.root. You run this run me, and you end up with si out.root, sm out.root, and with the analysis.jpg, same file because I have forgotten to change the file name to SI analysis versus SM analysis.
So these outs are selected events?
They are not events, they are histograms, and they contain what we have put in, remember. They contain, here they are written, they contain the JetPT, dijet invariant mass. Yeah?
But you didn't
Yes.
separate the contain, they contain same things.
No.
Which data is going to SM and which data,
Yes.
how you decide SM and
Here,
SI?
the decision is here. When I was running earlier with compap and modgraph, I did all the chain of delfs, PTR delfs, xroot analysis. I have created these two files, sm.root, si.root. Now here, when I initialize the class, if I say sm, with these comparisons, it reads sm.root. If I say si, it reads si.root.
Okay. It means SM.root you didn't add new particle actually. It is
Correct.
normal.
SM.root is the output of math graph, SI.root is the output of complex. Now we can, yes?
But maybe for those who are lost, you have to understand that this is what Gökhan is telling in particularly in the last two slides is a way to easily identify which input file you have and corresponding output file. Okay, so the code is related to that. The whole idea is to apply the same set of cuts on both your signal and your background. Okay, so he wrote one piece of code, and at the beginning of the code, it chooses: am I going to run all this code on top of signal, or am I going to run this code on top of my background? That's all what he does. Okay. So now he has two files, two output files with histograms. One we are going to see the signal histograms. On the other, we are going to see the background histograms.
Better?
Yes.
Excellent. Thank you. Now, as Erkcan said, we are going to do a comparison between the signal and standard model files. We need to calculate yearly event yields, and obviously they are proportional. These are proportional to cross sections of the signal and background, and we need to understand whether we can do a discovery or not. Remind you, the number of events was given by this formula: L for luminosity, sigma for cross section, and epsilon for efficiency. Now we need to write a code to do this comparison, and this is this code that we are going to look in detail. This is not very difficult. This is just one page. So let's look. Not difficult, please. Definitions. You start. Well, I named this thing compare because I'm going to do a comparison. Some definitions. The signal cross section 19, background cross section 60, luminosity per year. Here is a mistake. I am sorry for that. I should correct this. Remember when we discussed IIC's yearly luminosity was 28 inverse femtobarns. I should have written 28 here, but I forgot that and I wrote 10. Sorry for that. And I am going to count years, and let's look at 1 year at the beginning. And then I define a new window, new canvas. And here I'm reading, okay, let's focus in this one. I am reading now the output file sm-out.root. I am reading this, I'm going to read this file, so T file. I'm going to get out of this file JJ mass, the invariant mass of the two jets. And I am going to call this, I'm going to clone this histogram. And the clone will be called background mass for digest. BG, background mass of digest, MJJ. Right? In the meantime, I have written also in this file the efficiency of my cuts in the background, and I'm also going to read this one. Read from the file the histogram called efficiency, clone it, and rename it as BGF, background efficiency. Alright? Now, I need to do something. I need to do a scaling. Yes, sorry.
Is it for e-gamma conversion?
It was 28. We have calculated a few slides ago.
Yeah.
We have found it actually. E-gamma conversions, yes. It was 28 for IIC, but as I said, I forgot.
Inverse from
Yeah, it's wrong, I know. I was thinking of LHC and I wrote LHC. I'm sorry. I'll fix it. Okay, let's focus in this line, this scaling. So this contains the histogram that I want to look at. Alright? And I need to change this histogram because currently it contains entries proportional to the amount of Monte Carlo I generate. But I don't care about the amount of Monte Carlo. I'm not interested. I want to normalize things to n years of running. I want to say I have run my collider, took data for 5 years, 10 years, what has happened, show me. Therefore, I do a scaling of my histogram. So I am going to scale to the number of events that I expect. Hence, I multiply by my luminosity, by the amount of years that I have run, and by the cross-section. Just like the formula in the previous page. I am implementing exactly that. I'm calculating the number of events. However, I have started my Monte Carlo with some number of events, 5,000, 500, 50,000, something. And they were written in the first bin of my efficiency histogram. So I divide by this to normalize. Understood? Yes? And also, to make it look nice, I put the histogram color to red.
So
Yes.
you start from 1, not 0?
Start from 1. I do the same thing for the signal. Exactly the same thing. I get the same names because they carry the same names. Only the file name is different. And this time my variables are called signal instead of background. And my normalization here has the same luminosity, same number of years, but this time my signal cross-section. And it is of course normalized to the, well, unfortunately it is cut here, but it is normalized to the initial number of Monte Carlo events that I have started. Understood? Lost? Understood? Okay. Now, the rest is easy. I do something, I define something called total. What is it? It's a signal plus background. I'm adding my signal histogram and my background histogram. I do here some nice things to show number of events, to show titles of the x and y axis. And then I plot this histogram, the total. On top of it, I plot the background, and on top of it, I plot the signal. And then I save the final plot as final.png. Not very difficult. You can tell me that you won't understand this. I refuse. So I get something like this. And it's a bummer. Well, remember the initial value of my heavy W was something like 770, and at this point I don't see much. So I need to bring in a magnet to get rid of my haystack and retrieve my needle. So this magnet is the transverse momenta of my jet. I put here a new cut. I reject the event if the transverse momenta of my zeroth and first jet are smaller than 250 GeV. I'm sorry if you can't read it because of the colors. So I want my jets to be at least of 250 GeV transverse mass.
Most.
Huh?
Most?
Minimum. If they are smaller than 250, I say continue. Continue means skip the event. Then the rest is the same. You do the plots, you run for signal, etc. And you come here. You say W prime, nicely printed things, whatever. Okay. Remember, black is the total, red is the background, and blue is my signal. There is something here, but is this real? The question is this real or is this statistical fluctuation? Then I refer to your excellent lecture yesterday to understand whether this is real or not. We have to understand whether this is a statistical fluctuation or not. We have a number of estimators, and we saw that we measure the significance in sigmas. In high energy physics, 3 sigma meant an observation and 5 sigma meant a discovery. So we are going to see. But which estimator to take? Atlas and CMS these days are using this formula. And how do you do that? Well, you learn how to do fits in root. This is how you do a fit to the total. What are you fitting? A polynomial plus a Gaussian to estimate the behavior. I am representing my signal with a Gaussian. I am setting some colors, parameters in the range that I'm interested in. I am running a fit and getting the fit parameters here, and then plotting the resulting Gaussian distribution here separately. So I have used only my total distribution to do the fit, and I have only plotted the Gaussian part. So this is the kind of signal that I would like. I would say I'm getting. And there are two lines here to do something else. Why have I chosen a Gaussian? Because it's readily available. And also it gives me a mean value plus a sigma. And these few lines here are doing an integration of this thing, a Gaussian, around the center from my center minus 2 sigma to center plus 2 sigma. And this code is exactly doing that. And the number of sigmas from left and right are written here in this variable. Okay? We are coming to the end. We run this code now. It does the fit, and it tells me number of signal events is 20, and total number of events is 53, and number of background events is 33. You put into the estimator that we discussed, and it's about 3 sigma for I don't know how many years I have. So you say it's a signal, but for a discovery, we need to run longer time, and for that we have put the variable number of years. You increase it to something like 8 years. You rerun, and you get same thing rerun for longer, a significance above 5, which tells you that this is a discovery. Yes? Final word. Now you are ready to eat on your own style. The way to find your own style is to eat a lot. Therefore, all these accelerators, all these models are waiting for you. Work hard and be successful. That's all. So that wasn't hard, no? Hello? So, satisfied? Hello? Satisfied?
Yeah.
You wanted to see a full analysis?
Yeah.
Do you? Well, you think we missed some part?
Well, I'm sure that is only a small part of a normal definition of full analysis, but
I don't know. I let Erkcan answer this question.
Well, I mean, of course, there are many other things we can do even with this very simple model, right? I mean, we didn't do any cuts on the missing ET.
we did cut on missing ET. Here, missing ET greater than 20 GB.
No, I mean, like, it is not at the level to make a discriminant between your signal and background. That's what I meant.
Yes.
So, but in principle, it shows all the steps you wanted to do. That you define a set of cuts, you apply it to your signal and background. You at the end look at a variable in which you are expecting to see some sort of a bump, and at the end you see a bump and you make a fit to it and extract a significance from it. So it is indeed a full analysis, but each of the steps is of course extremely simplified so that we can all cover it.
So what?
We extracted sigma from the signal and background counts, right?
We did a fit to the total number of events histogram. We have added signal and background, obtained a histogram called total. We did a fit. We did a combined fit to that. Combined fit had two components. A component representing the background, which is a polynomial, and a component which is a Gaussian representing the signal.
We care about Gaussian.
We care about both because as a discriminant, we need to be able to estimate our signal candidates and our background candidates. making an individual fit to signal and background separately would be achieved.
So what's sigma? I don't exactly.
Sigma, in a sense, is your deviation. Is a measure of how likely you would get such a thing if this was a pure statistical fluctuation. Far sigma means you are 5 error bars away from the mean, considering this event being a deviation.
So we take the integral of number of events in the Gaussian kind of
to calculate it. To calculate what? Which Gaussian?
I mean,
The Gaussian in the error function or the Gaussian in the fit? Which Gaussian are we discussing?
in the fit.
In the fit? Okay. In the fit, this is what we
So
do.
integral.
In the fit, okay, maybe I was too fast here. In the fit, this is what we do. We say we integrate from here to here. That tells me the number of signal events.
So what's this 1 sigma? How do you integrate?
No. This is the total number of signal
Yeah,
events.
but from where to where do you integrate? How do you select your
From
number?
where to where? Okay. So this is the mean of my Gaussian.
Yeah.
This is a fit. The Gaussian has a mean and a sigma. Right?
1 sigma.
No. A mean and a sigma. Remember the definition of the Gaussian. Then it's up to you whether you want to integrate from 100 sigma to minus 100 sigma to plus 100 sigma, or as we did here, from minus 2 sigma to plus 2 sigma. Then that gives you the number of signal events. You do the same thing for the total function, which gives you the number of total events. You do the subtraction, you get the number of background events, and then you calculate this object, which is your estimator of the significance.
Okay, I mean, maybe there is one thing I can add to this. This is actually giving you a ballpark figure of what the significance of that bump is. Okay, under normal circumstances, of course, what you would normally to make it publishable, let's say, what you would normally do, you would only assume a background function and fit with it and get a probability of that fit. Okay, and you will take the other hypothesis, which is a signal plus a background, do the fit with that, and then compare the probabilities of the two fits and extract from that how significant the second hypothesis, signal plus background hypothesis, how significant that is compared to the background only hypothesis.
So first we just a linear fit, then
yeah, you could, for instance,
maybe we can remember the lecture about statistics that Jörg gave. You remember all these hypotheses? Maybe you should say something. H0s and H1s. You remember that? Now I hope it should make sense better at least. Please.
Well, no, I can't say much about this because I've never done anything sort of like this. I think actually knows better than this.
Okay, so in principle, as I said, it is a comparison of the signal plus background hypothesis versus the background only hypothesis. Okay. In the past, when we did these feasibility studies like this with Gökhan, we did a toy Monte Carlo study which showed that if we do this way and integrate between plus or minus 2 sigma, the significance that we get is very similar to the proper significance that you could obtain by doing the fully right thing. Okay. And since this is essentially a feasibility study, we don't have an IRC built yet, right? So this is to see how many years of IRC will be needed to discover such a signal. Then you can essentially do such a trick and quickly get estimated significance. If you're a simple theorist, well, then you would not even do such a thing. You would just say, okay, I see a number of signal events in this range between arbitrarily chosen 750 and 800, I don't know. And you would also say, in the same range, I see this many background events without with nothing at all. You would call just signal over square root of background. Okay, this is what you could. But this method is a lot, how do you say, more experimentalist-like. It has some reason for us to accept it as it is.
So which one is your null hypothesis? Signal plus background or background?
Well,
What was the question? I didn't quite understand.
So when you do this statistical testing, which one is the null hypothesis? Signal plus background or background only?
Background only is null hypothesis. Null means no signal.
And you try to recheck that.
You are trying to see whether your observed quantity, a distribution, a number, is compatible with background only or background plus signal hypothesis. Which one fits the data better? You ask this question.
Yeah, but there's an asymmetry between the null hypothesis and then the alternative hypothesis. So when you do statistical significance testing, you optimize it such that you're basically trying to recheck the null hypothesis, not to confirm the alternative hypothesis, right?
Maybe you guys should answer.
Well, I mean, in principle, if I understand your question right, of course, when you choose a hypothesis to check whether it is correct or not, or whether it is more viable. Okay, so if you want to compare two hypotheses against each other, and you are, for instance, behind a discovery, you want to make a discovery, okay, you will try to optimize your cuts and you will try to optimize your variables, etc., in such a way that you will have most likelihood to discover the event, to discover the physics if such a physics exists. Okay, so in that regard, the two hypotheses can be treated differently. Okay, but once you have defined the two hypotheses, the statistical test tells you which one of the two is more compatible with with the data. Which one of the two is more compatible? Okay, so I don't see any difference between the two hypotheses at all. So I mean,
it is like, you know, you should think about it like this. This observed distribution, if it was truly coming from the data, would it fit better to a line which is falling down, like a polynomial, or would it fit better to a line plus a Gaussian? You are asking, in fact, this question in layman's terms. And if it fits better to a line without any bumps, you say, okay, I'm compatible with the null hypothesis, no signal. And all these things actually depend on whether you want to do a discovery analysis or you want to do a rejection analysis. Rejection analysis has a different set of mind. The question asked in a rejection analysis is something else. Here you are asking the question whether the bump you are seeing is meaningful or not. There you are asking the question, how much can you increase without seeing a bump? It's a different thing. There you try to reject, it's different.
Yeah, this is exactly what I meant, that there's you have to decide if you're making a rejection analysis or a discovery analysis, and it changes the sort of things.
Okay, in this case you assume for the fit model Gaussian, right? So, for an observation, I guess the Monte Carlo should inspire you to select a fit model, right?
My inspiration came from the availability of root. Gauss was already there.
Okay, yeah.
Otherwise, driving as we have seen, is the right thing to choose.
Yeah. Sorry, can I interrupt? Okay, because maybe this also connects to the earlier question about how this is a full analysis. If you want, let's say, you run an HC and you get some data and you want to do an analysis and make a publication out of this, then of course this is not a full analysis. You don't have any systematics. You didn't say, okay, why I choose Gaussian as the model. I mean, there are so many things like that. And here, of course, this is a feasibility study. It is about a future, the possibility of finding a signal in a future collider. So here, also as an educational thing, we chose Gaussian because it is readily available, and if we want you guys to try the same thing on your own, you will be readily able to do it irrespective of your level of competence with root. But normally what you would do, first of all, there will be a motivation for a given signal. It is more likely to have a relativistic Breit-Wigner in such a resonance than than a Gaussian. On the other hand, of course, after your detector responds, if the width of if the resolution of your, let's say, jet, since we reconstructed this for jets, if your jet reconstruction, jet energy resolution is larger than the width of the Brightwigner, then your Brightwigner will be washed, and then you might actually get a Gaussian as well. So, I mean, there are all these things that you will have to consider when you do work on a real analysis.
So that's why I said, so you have to trust Monte Carlo to get this effects, right?
Yes, and the level of your trust, of course, will be reflected on how small your systematic error is going to be. I mean, of course, you'll have to do some studies. You'll have to understand, in a, let's say, in an independent control sample, how well your Monte Carlo represents the detector, well, let's say jet energy resolution, etc. And then you will get some level of confidence. That level of confidence will be represented by the errors, let's say, on the jet energy scale that you obtain by Monte Carlo versus data. And then you will, at the end, when you are about to publish, you have to convert all these uncertainties into the uncertainty at the final thing you get. Okay, I mean, there is, I mean, well, Gökhan said all the easy things are done, so this is the easy thing. For an actual publishable analysis, you will have to do a lot more work. Is that what you asked?
So we expect you to do something similar in tomorrow's game. You realize this now, right?
Why around 100 GB we have not bump but high?
Actually, you are talking about this bump, yes, around 100. Yes. Normally, you will see a continuous distribution starting from the peak of mass of W. But since we have imposed very high cuts on the jet transverse momentum, this high bump has been, this bump at mass of W has been pushed forward, and now it lies around 100 and something, 20, 30 something. That is the artifact of the heavy cuts on the jet transverse momentum. There was another question somewhere. Yeah.
If I have followed correctly, this full analysis you have used simulated signal, simulated data, and suppress and try to pull the signal out of the background, correct? And in real analysis, like Alex, you have the real data and the Monte Carlo data, and can you explain a little the philosophy of comparing the two, and how, what are the general things to look for when you decide whether the two agree or not?
Excellent, I take it. Okay, or yours doesn't matter. But I'm tired.
Okay, so when you are dealing with real data, of course, first of all, let's say I believe in the data there is a W prime. Okay, so that is how I start. That's like a hypothesis, and I want to test if this hypothesis is true or not. Okay. So what I need to do is I need to look at the right place in the data to see if it exists, right? So I start still with Monte Carlo. With Monte Carlo, I generate the standard model background. I generate this this possible signal. Okay. I do exactly all the things that is done here. I define, based on that Monte Carlo, I define what sort of cuts would make this possible signal to appear on top of the background. Okay. And after I finish up all the optimization, then I go to that real data and I just apply the same cuts on top of it. And then I if I'm lucky, I see a black line, light black histogram as shown here. Okay. And then over there I see, look, here is the bump, here is a possible signal. Okay. So the trick, of course, is to make sure that you do all your, you think carefully enough beforehand that you do everything to make the signal appear if it is there. Okay, because after you have made a decision on your cuts, and after you have looked into that and if you don't see a bump at all, that means you don't have the signal. Okay, you're done. If you 2 days later, if you realize, oh shit, I could have applied the blah blah cut and it would cut down on background so much more, you are biasing yourself because you already looked at the data, you didn't see anything, so you get upset, so you come up with a new set of cuts. Okay, so this is not right. This is you are biasing. Okay, but as long as you look at the Monte Carlo in advance, you think as hard as you can, you define your cuts, all your method all the way to the end, then you have the full analysis, you just come and just apply it onto the real data and look at the output. That's what you do.
Maybe something. You remember initially we started looking at trivial distributions like eta and phi distributions. When you are looking at the data, maybe the best thing to start is from here to understand, before looking at anything related to signal, try to understand whether your Monte Carlo is describing your data well or not. If this was data from a real collider, then here the first thing that we would do after plotting the eta of jets and phi of jets on top of this, we would plot the real data to see the compatibility between data and Monte Carlo.
But here I have to underline something. If you wanted to, let's say, compare the compatibility of data and your Monte Carlo, first of all you have to do this in an independent sample. Okay, for instance, you can revert your cuts so that you make sure there is, well, you're looking at the part of the data where everybody has looked already before and you know there is no signal at all. In that part of the data, you compare your, you tune and fix whatever your Monte Carlo, and then you do what you want to do with the part of the data that is most interesting to you. Okay, so this way, I mean, step one is to identify, let's say, possible parts of Monte Carlo that you might fail. Okay, based on previous experience, based on previous experiments, based on how other analyses went, etc. So you first identify what are the causes, what are the parts where Monte Carlo could fail. Then for each of those possible failure scenarios, you identify a control sample in data that has nothing to do with your signal. Okay, and then in those control samples you check that your Monte Carlo is properly representing the data, and if it isn't, you keep on iterating until the Monte Carlo indeed represents the data. Okay. And then with that fixed Monte Carlo, you do all these studies and optimize your cuts to or run whatever boosted and whatever multivariate technique you want to do. And on Monte Carlo, you identify a clear-cut way of how to extract the signal if that exists, and that you come and put onto the real data and make your discovery, or just make your 95% confidence level and make it. Well, you can still graduate.
I understand the logic, but the separate control sample that you mentioned, but yeah, it's a good idea. But I was wondering, well, there's another alternative thing that I just came with. I don't know whether it's acceptable or not. Let's say you have the data file, Monte Carlo sample file. You start before you make any cuts. Before you make any cuts, can't you just, let's say, plot, like without making any cuts, plot the distribution of all the BT or all the ET without making any cuts to see if they match or not?
Yeah, well, okay, you can absolutely do that, but then you won't be able to produce enough Monte Carlo, let's say. I mean, at the LHC, you have orders of magnitude larger events, more frequent events, that are, well, just basic QCD events. Okay, so if you wanted to like just take everything that comes from Atlas, but you will be hard pressed to produce that large amount of events that would come from standard model processes. Okay, so just comparing all data for practical purposes is not so easy to do. Okay. On the other hand, if you look at part of the data which is still broad enough, but not as broad, okay, that is a viable technique. So, for instance, if you know, let's say your signal has at least 1 muon, okay, then you have already cut down a significant part of the events that are pure QCD where you had only jets. Okay, so you can look at those events in the data where there is at least a muon above 15 GeV. Then you can practically produce equivalent Monte Carlo, okay, and then you can just put them together and compare. That comparison is only going to tell you how good your Monte Carlo is, because what in this comparison you are essentially comparing. So if you think about this needle in the haystack, okay, so you have the haystack here, and then here I make plastic like sticks, okay, that represent, this is the Monte Carlo of the haystack. So I produce, well, there's this huge amount of haystack, and I produce an equally huge amount of plastic sticks, and then I compare them. Oh, good, I made a good plastic haystack. Okay, that's all I. So this comparison doesn't immediately say, look, this side might have an additional needle in it or not. Okay, that comparison doesn't tell you, because the haystacks are both huge, either Monte Carlo or the data haystack. So once you start cutting down a bunch of the haystack that is on the data and the same amount of background in the plastic haystack, okay, then your comparison starts to become more and more meaningful. At some point, you have small enough, real haystack with the needle or without the needle inside, and a small enough plastic haystack. Then you can put them together on a scale and weight. Let's say, okay, let's say you take equal volume, you weight, and you find that the data is slightly heavier than the plastic haystack, even taking into account that plastic has a different density than the whatever you call it, the piece of haystack. Okay. So then you say, look, I measured the weight on this side to be 5 grams. On this side, I measured it to be 5 and 5.5 grams, and the difference is 0.5 grams. Is 0.5 grams statistically significant? Okay. So if your measuring device can only make a measurement with an error of 0.2 grams, okay, a difference of 0.5 grams is a 2.5 sigma fluctuation difference. Okay. So then you can say, oh, okay, this is maybe a statistical effect or not. So, does it make sense now? Okay.
We should stop.